We're always concerned about water hammer for both reliability, but especially for safety issues. What we're talking about with water hammer in a steam system is water being carried through the steam pipe and smashing into something, right? We should not have water in our steam system. We want steam in our steam system, and the water should be either not allowed into that system or quickly removed. Any condensate that forms in the system would be quickly removed by an appropriately sized drip leg and steam trap. So when we have an issue with trapping, or with the way we're starting up a steam line and we're trying to flow high velocity steam through a line that has water in it, then that water can get whipped up into kind of a wave, and when it seals the pipe off, it will smack into the next valve or elbow or trap or something of that nature. The easiest way to tell if you have water hammer is usually you can hear it, right? It's going to sound like somebody is taking a hammer and just smashing the pipe, but you might hear it several 100 feet away from where it's actually happening, because that stiff pipe can transmit that sound. So hearing water hammer, of course, is our first cause of concern, but that doesn't necessarily tell us exactly where it's happening, right? Everything's insulated and that pipe may be hard to trace out. So first of all, if we hear it, then we need to start thinking, okay, gosh, what's causing that? The other reason we might suspect water hammer is we can see the damage that was caused by water hammer. So even though we didn't hear it, we might open up a float trap and find that the float has holes in it, and so it no longer floats. Or if we have like a thermostatic trap that's got a bellows in it, and we find that those traps are going bad quickly and failing open, right? Well, that could be from water hammer damaging those components. So what causes it? On one level, what causes it is just water in our header or water in our steam line. Typically, we're going to size a water line for 10 feet per second as a maximum for a water line. Whereas a steam line we might design for 200 feet per second if it's good dry high pressure steam. Low pressure steam is going to be typically less, just to keep it quieter if it's in a heating system in like a campus or something. That high velocity is really reserved for gases rather than liquids. So you put that liquid into a high velocity line and you can really start to erode the piping or cause some major issues. What puts water into our steam system? First of all, water in our steam system is normal if it's a saturated steam system. As heat moves through the wall of the pipe and through the insulation, we're going to form condensate, right? Saturated steam can't give up any heat without forming condensate. And that condensate should flow along in the direction of the steam. That steam pipe should be sloping downhill with the flow to the next drip leg. In that drip leg, we should remove that condensate through the steam trap and send it back in our condensate return system. So if we have a trap that's failed closed, we're going to have water buildup in that header, and when the flow increases, we can have a water hammer event. It can be pretty damaging. It can be quite dangerous. People die from water hammer issues and pipes and valves coming apart. It's a real issue. But a big one could be even just startup. So, a trap is sized. Your typical trap in a steam system is sized for running load. So that running load, when the pipe is already hot and the pipe is well insulated, you're not forming very much condensate. But if you took a cold header and began to put steam into it and warm it up, now as you warm that, several thousand pounds of steel in that steam header, you're creating a lot of condensate in that system and trying to flush it through a trap with a teeny tiny orifice that really was intended for just that small continuous load. So it may be a trap that's designed to move a few gallons an hour and you're giving it 40 gallons an hour in that warm-up hour. It just can't flush that out fast enough, and if the drip leg's not large enough to store that, it's going to get sent down the pipe and bang into things. So really the biggest time to be on alert for water hammer is when we're starting up a cold system. And the best way to prevent it is making sure those traps work right, but also making sure we're manually draining those drip legs or opening those trap bypass legs and things like that, so that we're ensuring that system is completely hot and completely drained before we try to flow significant amounts of steam. So we need to get that distribution system hot, drain it all down before we bring process online, or we run the risk of not having everything drained and really water hammering. Typical cause of water hammer would be boiler carryover. When we have carryover, that would be boiler water leaving the boiler. We only want boiler steam leaving the boiler. So when water leaves the boiler, now that water is going to bang around in our distribution system. The most common reason for carryover is bringing steam load on too fast. If I have a fire tube or a water tube boiler and a load comes online really quickly, it will lower the pressure in the distribution system and in the boiler, causing the boiler water to flash, causing the boiler to ramp up in rate, and causing the water level in the boiler to climb so much that it actually hits high water alarm or higher, and it's priming or physically pushing water out of the boiler into the system. That's way more water than that system was designed for. Another common cause of carryover can just be bad chemistry. If we have way too much chemical treatment, or we allow the boiler water conductivity to climb way too high, those can affect the surface tension of the water itself, which will kind of cause that water to be kind of soapy. So now we should have bubbles popping and separating and good dry steam leaving the boiler, and instead we're making soap bubbles and flushing soapy, foamy mixture down the pipeline. Well, that's going to carry a lot of water with it too. And so then that can cause water hammer. The way we prevent that is obviously watching our water chemistry really close. On the carryover front, if we suspect that's an issue, carryover is really easy to diagnose by looking at our condensate conductivity. Steam condensate is essentially distilled water. It should be very pure. It should have very low conductivity. So if we see that in certain operating situations, our boiler water conductivity is steady, but our condensate conductivity is shooting up, well, the reason that our condensate conductivity shot up is because we mixed in some boiler water with it. So when we carry over and mix in all of the minerals that were in the boiler water with that clean condensate, we're going to see it right away. It's pretty common on daily boiler log sheets that we record a condensate conductivity, and that's the reason we do that. We're looking for signs of carryover, which would be a high condensate conductivity. Typically indicates carryover. That's kind of the nuts and bolts of water hammer. Like I said, it can be very dangerous, it can damage equipment, but more importantly, it could cause a flange to break apart. And if you've got high pressure steam inside that valve or flange or system, and you're near that thing when it comes apart, steam is very good at giving up the heat that it contains, and it can be catastrophic for anybody that's nearby.